But our first speaker today would be Dr. Ahmari, sorry, Habib Ahmari, and he's a associate professor in the Department of Civil Engineering at the University of Texas at Arlington, and he's also a licensed professional engineer like a lot of us. He's in both Texas and Ontario, Canada. Dr. Ahmari has over 20 years of experience across industry, research, academia, and his expertise lies in water resources engineering. And before joining UTA, he spent a decade in Canada leading environmental impact assessment studies for hydroelectric dam construction projects. And his research focuses on environmental hydraulics, sediment transport, stormwater quality, and stream restoration. And this morning, his topic will be designing stormwater treatment BMPs, bridging physical experiments, and the numerical modeling. Let's welcome Dr. Ahmari.
So much for the introduction. Can you hear me well? I need to. Sure, I'll do that. Thank you. Thanks for the introduction. Today I'm going to talk about some research we are doing at the UTA. This project has been awarded to us by NCT COG. So in this project, we had a few people working with me. I mean, they do the work, I present the work. That's how it works at the universities, you know. My postdoc, Sam, and my master's students, Ashish and Kasi, work with me on this project. So as you know, the non-source point pollutants is the #1 source of pollution in US waters. The 9-point source that I'm referring to, those are the sources that we have multiple areas that bring contamination or pollutant to our waters. Those are very challenging topics because identify those sources are very difficult, mitigating them are very difficult, and treatment is also very difficult. As you know, what we do in practice, we install waste management practices. There are many of them to capture the sediment or other type of pollutants. One of them are bioswales. So bioswales, basically we install them close to the roads to capture whatever is washed out from the roads and then treat them before sending the water to the US waters. These bioswales have some issues, mainly because of the clogging. So the lifespans are very short. So in this project, we have introduced a new material. I mean, the material is not new, but we introduced the idea using expanded shale in the design of bioswales. Rather than doing the design based on whatever is available in hydraulic design manuals or storm design manuals, we used physical modeling and numerical modeling to see how this material can perform and what are the efficiency of this material. So this is about the talk we are going to have today. Next slide, please. So this is the outline. We're going to have some talk about the background, approaches, and objectives of the project. I'm going to talk about the experimental setup that we had at the UTA to run this experiment, and also numerical modeling approaches we took, and finally result and some conclusions. Next, please. So as all we know, if we transfer the natural land to an urban area, there are two things would happen. First of all, we are increasing the runoff by introducing more impervious surfaces, and also we're introducing more contamination with the roads, the buildings, the pavements, everything. Basically, we are introducing more sediment, heavy metals, nitrogen, phosphate, all kind of stuff that we are releasing from this urban area. So these material, as I said, we don't want them in our water. We try to, first of all, reduce the volume or peak of the flow to the BMPs and also reducing the contamination. So there are two different type of BMPs. The bioswales are linear BMPs that we can construct them along the roads to do this job, mainly to reduce the contaminations. Next slide. So the bioswales are a linear shape. The way they reduce the contamination, there are two different processes. First of all, as we know, is a sedimentation, meaning that sediment would trapped in the bioswale, and then is by filtration, water would filter to the bottom of the soil. So it's going to capture the contamination, including sediment and other contamination. The third one is basically uptake by the plants, if you're talking about bioswale, meaning that we grow the plants, and then we have absorption and infiltrations. So in different parts of the US and world, we have seen the effectiveness of this bioswale that are working, but the major problem with this bioswale is clogging. After the few years, when the surface is clogged by the sediment captured bioswale, their efficiency would reduce. So there have been some studies in Maryland saying that out of 27 bioswale they installed, 1/3 of them failed because of the clogging, meaning that in the few years, so basically you have to just go and scrape the surface or replace the medium to increase their efficiency. The reason that we have this clogging is basically because of the size of the material we have in the native soil, and also because of the infiltration rate that is limited the seeking the water through the soil and treating the flow. To resolve this issue, what we can do, we can replace the native soil with the more porous medium. One practice would be adding sand or gravel. But these sand and gravel, if you add too much sand and gravel, the infiltration is going to be very high, and then you cannot grow any plants. And that's not a good thing in Texas because we don't get a lot of rain. If the soil cannot hold water, so the plant would not grow. So we are failing our purpose. The idea in this project was to use, instead of the sand and gravel or crushed stone, use expanded shale. So expanded shale is a new material that's been used in different industry. So we thought that would be the opportunity to test the expanded shale in the design of bioswales. Next slide, please. So one back, please. Okay, expanded shale basically is, next, it's just that there's a lag here. Next, please. So expanded shale is nothing but clay. We heat up the clay at very high temperature and make it something very light and porous. Some sort of granule material is very light. So in this picture on the top, you can see the gravel size of expanded shale. On the bottom, you can see the sand size of the expanded shale. Expanded shale has been used in many practices. One of them would be improving the infiltration of the clay. Clay doesn't have a lot of infiltration. In textile practices, when they build roads, they use expanded shale to enhance the infiltration of the clay. Other application of the expanded shale has been in water-based treatment facilities and also some other treatment as a sand filter. Instead of a sand filter, they use expanded shale. Some of the properties of expanded shale, we can see here, a specific density of the expanded shale is much smaller than of the sand, as well as permeability. Permeability is very high comparing to the sand, so is perfect solution. Probably in our work, that's we're gonna to see how that's gonna help us with the design of bioswale. Next slide, please. So the objective, so similar to any other problem we deal in our life, we have a problem in real life, we're going to solve the problem. How we solve the problem? There are many different approaches. One would be looking at the conceptual problem, conceptual solutions. Conceptual solutions are very simple. Either you can use a simple formula to solve a problem or put that formula Excel sheet to solve a problem. It's very simple, low risk, low cost. Some problems are not that simple. You cannot solve with the conceptual problem. What we do the experimental work, either in the field or in the lab. Experimental work would work, but it's always more expensive. You have to build something, either the full scale and test it, or you can test it in the lab. The cheapest way of doing the work is numerical modeling. You sit at your desk and then do the work, but there's always danger about that. If you do not have good data, if you do not have a calibrate model, the result might not be what is really is happening. So in this project, we took two approaches. Next slide, please. So first of all, the objective, we wanted to evaluate the application of expanded shale as the amendment in the design of bioswale to see if it can be working for a stormwater treatment in transportation industry. The approaches we took, we installed the bioswale in the lab and monitored its performance under different conditions, including different hydraulic loading, different sediment loading, different thickness of the bioswale, and also different size of the bioswale, different size of the material. And then we measure the water quality at the beginning of the flume or soil, in the middle, at the end. The water would go over the downstream as an overflow. The water seep through the filter, underflow, and then we calculated, obviously, the efficiency of the soil under different conditions. And then based on this result, we had some data. We developed numerical model to see if we can do more testing. So as I said, the experimental work are expensive. One-to-one scale is so expensive in the field, so we can do in the lab. But lab also, for the design of soil or install the soil, you need a large facility, and you need to have a larger space to do the testing. And we are fortunate that UTA, we have that facility. We have a large river flume. We can simulate both hydraulic and sediment transport, and that gave us the opportunity to run these experiments. So next slide, please. Next, okay, there you go. So on the left side, you can see our experimental flume. On the right side of the flume, you have the intake tank. Water is coming from the sump and then would enter the flume. The flume is 16 feet long, 4 feet wide. And then at the end, we have the outlet tank. The water would come back to the sump, sediment would be captured, and then we have the recirculation. And then on the bottom of this figure, you see a slurry tank. We had this tank, we add sediment and water, we mix them, we create a slurry, and the slurry was pumped to the beginning of the tank and added with the water to create the desired total suspended solid. We added silica flour to simulate what is coming from the roadways to the to the bioswale at different rates. The flow rate could have been different. We look at different flow scenarios. On the bottom of the tank, bottom of the flume, we see a brown area. This is the filtration or medium, which is include the expanded shale and sandy clay material, 65% 65% shale, 35% sandy clay soil. At the end, we had a facility to capture the water, but before that, we have a weir to flow would go over the weir as we have in our all biosoils, and then water would seep through the soil on the through the soil or biosoil, and then we have overflow, excess flow that cannot seep through, and then we have underflow in this case. On the top right side, you can see the entrance of the flume. So sediment is going to be mixed as a slurry with the incoming flow, creating the stormwater, with stimulating stormwater, and would go through the whole length of the soil. At the end, you can see the weir, and then we see the out drainage pipe. Underneath of these plume, through this expanded shale, we have developed or installed a drainage system to improve the filtration, just like similar we have in practice for bioswale. You install a perforated pipe to increase the infiltration. So we had two options here. We could close the valve at the end, no infiltration system in place, or infiltration in place. Next slide, please. So this is the whole view of the flume. As I said, we have the end weir and we had the outlet to separate what is going through the soil and what is going over the weir. So we wanted to see how these two would act. The first type of sediment removal is sedimentation. So what percentage of the sediment reduction is due to sedimentation, and the other part would go through the soil. What percentage is due to the infiltration? Next slide, please. So this is the shot of the flume is running. On the bottom side, you can see the little bit darker area. This is the shale, and the top, the flow is running with the sediment carrying by the flow. Next slide. So this is the intake area. So you see the slurry is going through this perforated pipe across the flume, is mixed with the water coming from the sump, and is creating different suspended solid. Just to reiterate what I said, we not only look at the suspended solid, in this case, we also look at the nitrogen, phosphate, and zinc. So we introduced them. I'm not going to present those results. We had some preliminary results that are not very conclusive for the other pollutants. Today, I'm going to just present the result about how much TSS, total suspended solid, could be reduced, and also the turbidity. Next slide, please. This is the outlet. As I said, a portion of the water would go through the weir, the end weir, and the other one would go through the infiltration. This is the case when you have a high flow. You know, the soil would act differently if you have very high flow. So you have overflow. If the flow is, let's say, average flow, or let's say 2-year flood or rainfall, everything is going to capture to the filtration. Next slide, please. So to assure that we have a biosoil, meaning that something would grow, this is the plant voluntarily grew in our lab. We didn't try. Yeah. Next slide, please. So we look at 30 different scenarios. First of all, we had type 1 coarse media, type 2 fine media, meaning that we mix the soil, the sandy clay soil, with the gravel size shale, and also the second type we use sand size bioswale, sand size expanded shale. So we have type 2 and type 2, two different scenarios. Then we look at the two different thickness for the filter media, 6 inches, 4 inches. In practice, the minimum size is about 12 inches for infiltration. But we didn't have that opportunity because of the limitation of the height of our flume. We just look at two different scenarios, 4 and 6, to see how that would change the efficiency of the system. Then we look at the drainage condition. As you saw, we had a perforated pipe underneath of the system to improve the drainage. We had a case, we closed the valve. The other case, we opened the valve. So two different drainage cases. Then we look at the hydraulic loading, 6 liters per minute, 120, and 180. The middle flow under 20 was based on 5 minutes resident time in the flume. And that's basically based on the recommendation by Caltrans, saying that if you're designing bioswale, you have to have at least 5 minutes resident time, meaning that sediment should have stay around 5 minutes. So that's 120 liters per minute. The 60 is based on another recommendation saying that you have to keep your residence time for 10 minutes. So we have 60, 120, and then 180, basically looking at the higher flow. The 120 replicate half an inch per hour rainfall in the area. 180 replicate something close to 10-year rainfall in the area. And then eventually we had two different sediment loading, 100 milligram per liter, 200 milligram per liter. 100 milligram per liter is common concentration for the sediment coming from the roadways, especially in Texas. There have been a study by UT Austin back in 90s. They captured or they estimated or measured the TSS coming from the roadways at the level of 100 milligram per liter on average. So we look at the 100 milligram, and then we said, worst case scenario, if you have much higher sediment coming from the roadways. On the right side, you can see the gradation of the material we use. The G pile refers to the coarse expanded shale. J pile refers to the sand size expanded shale. Those are the terminology used by the manufacturer. And then when we mix them with the sandy soil, we have type 1 and type 2, the dashed lines. Next slide, please. So to study the fluid dynamics in the flume, I'm going to say why we were interested to look at the fluid dynamics. We look at the particle image velocimetry, or PIV. So the PIV system is non-intrusive method for measuring the fluid dynamics in a system. So that's what we did. So what we do, you install several cameras if you want to do the 3D image of the fluid dynamics, or you can put one camera or two cameras to look at the 2D flow condition in the system. So in our case, we installed one camera, but at 3 different locations, one close to the entrance, one in the middle of the channel, one towards the end, to have a 2D view of the side view of the flow in the soil. So you put the camera, and then you need the laser sheet to make sure that you're capturing the fluid dynamics at certain location that you want to. So the laser sheet is shooting from the top, the camera is shooting from the side. You have the 2D view from the cross-sectional view of the system. So the result from the PIV could be basically velocity vectors, streamlines, and shear stress, if you are interested to know about the fluid dynamics. Next slide, please. In terms of numerical modeling, once we completed our experimental work, we did numerical modeling using Flow 3D. We replicated the exact size of the lab in numerical modeling here. So we have two medium here, both of them porous medium. The brown one is basically the infiltration system we have, including bisoil. At the end, we had the box that we had the gravel in it. So we took the result from the lab here with the porosity of 0.9 for the gravel and 0.2 for the gravel at the end. And then we ran this numerical simulation to see what we can learn from this 3D modeling. Next slide, please. So for the Flow 3D, we not only look at the flow dynamics in terms of the hydraulic of the flow, we look at the sediment transport, but at two different scenarios. First, we assume that the bisoil is clogged, meaning that there is no infiltration. If there is a sediment trapped by the bisoil, is just through the sedimentation or settlement. So we took the bottom of the flume as a solid surface, and then we ran the scenarios. There are some limitations with the Flow 3D. We could not simulate the whole range of sediment that we introduced to the flume in terms of size. We could only introduce one size. We look at the D50 of the material, and we introduce it as sediment incoming to the system. We did some tests to see how long would it take to get a steady state situation. in the model, and it seemed that we needed to run the model for 1,000 seconds first to get a steady state. Then we can look at the efficiency of the system. We ran 8 different scenarios, 4 of them with a solid bed and the other 4 with the porous bed. We look at 2 different scenarios in terms of the flow rate. We look at the low flow rate around 60, the other one 180 for both of them. And then we look at 2 different sediment concentration, sediment loading, 100 and 200. So overall, 8 different scenarios. Next slide, please. So results. The result from the experimental flume, as you can see here on the right side, on the left side, the top left side, the sediment is coming, that's one example, at 100 milligram inlet, the top dash line. And then the very bottom one is the outlet. The water is sipped through the soil. And in the middle, we have 2 lines. One is the green, the other one is orange. So one is the data that we captured in the middle of the channel, and the other one is from the overland flow. So basically what we have done, when you're running the experiment, we ran it for 40 minutes to make sure that we have enough resident time and the flow is a steady state. And then once we were comfortable with the running, we took the sample every 10 minutes, and then we took 1 sample from the beginning of the flume across the channel, 1 sample capturing the whole thing across as an average, 1 sample from the middle of the channel, the other one from the overflow through the weir, the other one underflow. So we have 4 different locations. Then we did the testing in the lab to see how much TSS we have. So if you have 100 milligram at the beginning, how much we have at the outlet. So the difference divided by 100, that gives you the percentage of the efficiency. So we did all this calculation for all scenarios. On the bottom side, on the right side, top right side, basically, you have the turbidity. You see the reduction of turbidity, but it's not very consistent comparing to what we have for the TSS. So the top two figures showing the result for 6-inch thickness of the material. The bottom 2 are for 4 inches. So both of them showing promising result for reducing TSS, but obviously the 6-inch is showing better performance. Next slide, please. So here in these figures, we see how the total suspended solid reduced along the channel. So our channel was 16 feet, as you can see at the beginning of the channel. The time 10 minutes from the beginning of the experiment, at the time 40 minutes after the experiment started. If we had the 100 milligram at the beginning, at the end, we saw something close to 40. So this is the change in the total suspended solid concentration along the flume. So it shows some improvement in terms of whatever water is going out. In the middle figure, on the top, you don't see that trend specifically for turbidity. It shows that it went down for 10 minutes, but then it picked up at the end. So meaning that turbidity was increased, even though the TSS was reduced. On the bottom figures, the first one on the left is showing the same result for 100 milligram per liter. And then the middle one is showing the turbidity reduction for 180 milligram per liter. Again, there are some reduction for TSS and turbidity both. And on the right side, you see how the sediment sizes changes through the system. When we introduce the sediment at the inlet, so you see the blue lines, it's coarser, even though we call them all silt, but it varies from, let's say, 64 micron to all the way 10 microns, everything. Then as sediment move along the flume, drops the larger one and gets to the end. So you see smaller size of sediments in the water. So that shows how this process of sedimentation would work, or infiltration, both. So you have the result from the middle of the channel, and then also we have the underflow, meaning that through the infiltration, and you have the overflow, the water would pass through the end weir. Next slide, please. So this is basically looking at the many variation of scenarios that we had. On the top left, you're talking about the 6-inch soil media. On the right side, we have the result for 4-inch soil media. So I packed everything in one slide here. We look at sediment loading from 50, 100, 200 milligram. You see the result, different colors. Then we have 3 different hydraulic loading, 60, 120, 180. You see a trend here. In general, 6-inch perform better than 4-inch medium in terms of reduction of the TSS. The other result we can see here, basically, the flow going through the expanded shale capture more sediment comparing to overflow, especially if you have high flow. The sediment is pushed through the system, and is going to leave the soil. We didn't see that much of a uniform trend for turbidity on the bottom 2 figures. In some cases, even the performance or percentage of reduction of turbidity was negative, meaning that the turbidity was even higher at the end of the flume comparing to the inlets of the flume. So the summary of what we found for all these 30 scenarios is in this table. So 4-inch, if you have 60 liter per minute, the reduction of the turbidity was 56%. 120, there's a reduction in the efficiency to 40, and then when you push the flow to high 180, you get even a smaller performance. When you go with the 6 inches, obviously there is the improvement in TSS removal from 56 to 66. For 60 liter per minute to 33 to 36. So those are not significant differences, but overall, 6 inches of the bisoil with expanded shale perform better. So we decided to continue with the 6-inch, not doing any other tests with the 4 inches. Next slide, please. So now we look at the effect of the drainage. If you have that perforated pipe, active or inactive, how that would help. On the left side, we have the system without the under drain system, meaning the valve is closed, the pipe is not working, is not helping the infiltration. On the right side, we have the valve is open, and then we look at 2 different cases. We look at the efficiency of the TSS removal when we look at the underflow through the infiltration, and with the overflow through the weir. And obviously, you can see a trend when we have measured the efficiency for the underflow, we have better performance, meaning that the sediment passing through the expanded shale is captured significantly, but not with the overflow. And that makes sense. So especially with the smaller flow rate, most of the flow would pass through the infiltration and increase the overall efficiency of the system. When you have a higher flow, the flow doesn't have enough time to infiltrate through the expanded shale or the filtration medium, so it passes through the weir, so it causes less efficiency. Next slide, please. So again, we put everything together, look at the weighted average of TSS at T removal, turbidity removal for the 6-inch bisoil with regards to several things. First of all, on the figure on the top left, you can see the weighted average TSS reduction with regards to type 1 and type 2, as well as the flow rate. As you can see, with the increase in flow rate, the system was less efficient in removing the sediment from 80% all the way to 40%. When you have 60 liters per minute, we have 80% removal, which is very close to what is required by EPA for TSS removal before sending water to US water. But when you're dealing with the high flow, 10-year flood coming to the system is not as effective as low flow condition. On the second one, on the left side, we are looking at the with and without the drainage system. As we discussed, when you have the drainage in place, you're increasing the infiltration rate, so the efficiency of the system is better. So we can see the orange curve is above the blue one, meaning that adding the perforated pipe to the soil would improve its efficiency. The third one on the left is showing that the effectiveness of the system with regards to 100 milligram or 200 milligram sediment loading. And the system performed almost the same, meaning that regardless of the sediment loading, the soil would perform almost the same. We have the same result for the turbidity on the right side. Again, type 1 and type 2 perform very similar when it comes to the turbidity removal for different flow conditions. Better performance with the drainage system in place, even for turbidity, as well as some differences between sediment loading with regards to the 100 milligram, 200 milligram for turbidity. But overall, we see a trend. There is a reduction overall in both TSS removal and turbidity removal when it comes with the increase in flow. The summary of the result is also, just if you're interested, the numbers are summarized in the table below. So we see for type 1 and type 2, we have for 60 liter per minute from 70 to 72% reduction, all the way down to 41 to 39% reduction in TSS removal, with and without the undrained, from 67 to 76, 66, 76, all the way down to 34, 47 reduction. Next slide, please. So this is basically the summary of all the figures and all the scenarios that we have seen today. If I wanted to measure the TSS removal efficiency from the beginning of the flume to the middle of the channel is 42%. So 42% of the sediment would drop out or would be filtered if you just basically are in the middle of the channel. The channel is 16 feet long, so we are in the middle. And then through the overflow is 43, meaning that from the middle to the end, the sedimentation rate didn't change, the efficiency didn't change. For the underflow, we have 68%, meaning that more flow seeped through the bottom, and then we got better reduction in TSS. And the percentage-wise, these are the average value, but the range was from 20 to 75%, depends on the scenario. For overflow, 19 to 57, 75, that's a range value. And for the underflow, the range was 52 to 82%. And then for the turbidity, as you can see, the removal was much smaller comparing to the TSS, 18% versus 42, 17% versus 43, and 40 versus 68. So if you look at the industry, in many cases, we use turbidity as a surrogate for suspended solid. It's much easier to measure turbidity comparing to suspended solid. Turbidity, put your logger, and in real time, you can measure the turbidity. But TSS, you have to take a sample, take it to the lab, do a lot of testing to get the TSS value. So in this case, it seems that turbidity cannot be a one-to-one representation of what we have in the system. And also the problem here, you see there are some negative values, meaning that the turbidity picked up instead of being reduced through the system. Next, please. So basically, this is showing the variation in turbidity. As I said, in some cases, you see the reduction between 10 minutes and 40 minutes time step, but in other cases, we had an increase. I'm going to talk about why we saw this situation. Next slide, please. So can you click, please? So this is the video we took from the flow when it was running. So you can see the flow is from your left to the right, but you can see the sediment is moving towards upstream. So there is a recirculation happening in the system. So sediment is not leaving the system. It's a good thing, first of all, because you have more resident time, but at the same time, is increasing the total suspended solid at some places, and turbidity, as we saw, is not showing the reduction. So when we saw this video we captured by naked eye, we thought we need to do something. Maybe we can have more investigation about the flow dynamics in the system. So the bottom figures, can you click a few times? So the first one is running on the right side, is showing the video we captured with the PIV. Flow is from your right to left, and the sediment is also from in the same direction as the flow. Click, please. The middle one is showing the middle of the channel. Maybe, I don't know if it's very clear or not, but the sediments are wandering around. They don't know where to go, to the left, to the right, to the top, because there are eddies are forming the system. So we saw that circulation. Next, please. This one is at the end of the channel. This shows that the sediment is moving from downstream towards upstream. So for that reason, we thought we need to look at some investigation about with the PIV. Next, please. So this is the result from the PIV. Flow is from right to the left, inlet area, middle section, overflow area, downstream. We have two different scenarios, 60 versus 120. So you can see with the 120, flow is mainly from right to the left, except for the middle one. Flow is pushing all the way, is trying to leave the soil, except for the middle one. You see the eddies are forming. But for the low flow, flow is going downstream, hitting the downstream weir, and is moving back and bring the sediment to upstream. So it's basically adding more resident time, improving the efficiency, but at the same time, the turbidity is increasing because the sediment is picking up from the bed and adding to the turbidity of the water. Next slide, please. So we look at the flow 3D, but before running the flow 3D, we needed to validate or calibrate the model and validate the result. So we look at two different cases, a solid bed. We try to match our observation for the flow depth with the flow depth in the model to make sure that the results are validated. And then in terms of the bed with the porous material, we try to look at the amount of infiltration rate through the soil and also overflow to find a match. Once we're comfortable, we decided to run the experiments. Next, please. I'm going a little faster. Time is coming up, right? Okay, so we ran the flow, and then this is showing that why we picked the 1,000 second for running. So it's showing the top one, 1 second after the starting the model, 100, 500, 1,000, and then based on this experiment, this trial, we found that we have to run all the experiment for 1,000 seconds, make sure that we have a steady state scenario, then we can compare inlet outlet to come up with the percentage of removal. Next slide. Then we ran the system with the solid bed. This is the result with the solid bed showing the sediment distribution along the flume. Obviously, you have the source on the left side pushing the sediment, but sediment is dropping out, and then we have less concentration throughout the system. Next slide, please. And this is basically the average of the total suspended solid along the flume. As you can see, the two solid lines are for 60 milligram per liter, 100 milligram, 60 liter per minute, 100 milligram, 180, 100 milligram. So we have two scenarios, two loadings, two different flows. So overall, 4 different scenarios, as you can see, with the smaller flow rate, you get higher efficiency. Starting from 200, you go all the way to, let's say, 100. It's about 50, 60%. And then from 100, you go all the way to 60, 40%. So the numerical model replicated what we saw in the lab with the same exponential trend in sediment removal throughout the system. Next slide, please. And this is the result in terms of percentage removal with the solid bed from 89%, with the 60, the lowest flow rate, all the way to 54, for the highest flow rate, 180. Next slide, please. This is the result with the porous medium, meaning that this water would go through the soil as well as on top. So this is probably the first work with the Flow 3D, looking at the interaction of the subsurface flow and overflow. I haven't seen this before. The company called us saying that let's talk about this one. Is going to call it the feature experiment. Never been done. So we push the limit of Flow 3D, and we look at the interaction with the flow and the sediment going to the soil. It's not just a flow going to the soil, it's both of them. So these are the results for 4 different scenarios I mentioned. Next slide, please. So this is the result basically. On the left side, you see 4 different scenarios for 60 versus 100 liter per minute, as well as 100 milligram per liter versus 200 milligram per liter. On the left side, you see what we see as the overflow on top of the soil. On the right side, what you see is through the soil. So we measured through this CFD modeling how much sediment is basically running through the system at what percentage, at what concentration. So you see in overflow, sediment is decreasing, obviously, because of the settlement, but in the underflow, sediment concentration is decreasing because as the flow goes through the soil, more sediment is captured, and you see more concentration inside the soil. But the outlet definitely is going to be much smaller. Next slide, please. And this is the result in terms of the percentage removal for all different cases here. We look at the porous bed. Again, the highest value is 82%, as we saw, close to what we saw in the experiment. The lowest one, 51%. Next slide, please. So this is basically showing the sediment concentration through the soil and flow dynamics through the soil and above the soil. So that is not only showing how sediment is moving through the system, is showing in what direction flow is moving. I have highlighted 3 different areas that we had the PIVs, beginning of the channel, middle of the channel, at the end. As you can see, for the 60 liter per minute flow, which is basically above the yellow line, is moving back towards the entrance. So it's replicating what we saw in the lab. But the flow through the soil is going towards the outlet. So they're acting in 2 different directions. Next, please. This is for 180 milligram. As you can see, above the yellow lines, flow is always going from the left to your right, meaning that flow is pushing through the system, and then sediment concentration increases towards the end. Next slide, please. That was the last one. So conclusion, TSS and TU were reduced by 82% and 65% in water infiltration through the expanded shale media, and 75 and 49 in water through the outlet area. The 6-inch performed better than 4-inch layer in terms of reducing TU and TSS, and adding on the drain help a lot in terms of reducing the TSS in the flow. Type 1 with the coarser sediment or coarser shale perform better than the finer one. And then as the inflow rate increased, the overall efficiency of the soil decreased, as we saw. An increase in the influence sediment concentration didn't change the performance of the system. And overall, with the soil, with the expanded shale, showed promising performance in removing suspended solid, comparing to other type of material, especially the sand. Next one, please. So basically, this is talking about what I just talked about, the CFD. CFD can be used to better understand the fluid dynamics of the system. We cannot simply use an equation to size the bioswale. We have to look at the dynamics of the flow, the location of the viers, or if we need to have some sort of, baffles to redirect the flow to make the better efficiency. So it's recommended, we are recommending to using modeling rather than just using a simple equation to design a bioswale. Next slide. And I promise this is the last one. References, next one. The project was funded by NCT COG. We appreciate the support, and also the material was donated, the expanded share by Arcosa, and we appreciate their support. Okay, any questions?
All right, guys, really appreciate Dr. Ahmari for very informative presentations. So, we started a bit late, so I think we're still fine. Don't worry about the people walking around. That's their job. So we are doing our job. So anyone have a question? Let's say like maybe up to 2 questions. Anyone? Okay, great. Thank you, Boniface. So we do have an online question for Dr. Ahmari. Someone asked, did you investigate how long it took to clog the system with the filtered particles? Also, how would the root systems of the plantings that are common in bioswales affect the flow? Sure. How the root systems of the plants will affect the infiltration and the flow, from the plants.
Thanks so much for question. We did not directly investigate the clogging, even though we tracked our drainage system. Each time we knew how much flow is coming, and we measured the overflow and underflow. We didn't see much of clogging, but to prevent any issue with the clogging, each time before running the experiment, we scrape the surface, making sure the clogging is not happening. But that's a major question. We needed to run the experiment for the longer time. This is only happened in few months, but in reality, a soil would last for several years, so we had to keep track of that. Yes, but we did not track that one. In terms of the root, we did not investigate the roots. We did not have opportunity to plant anything, but definitely that would be a good topic for investigation.
All right.
For the slope of the soil, we followed again from Caltrans. The minimum required slope is 0.3%. We tried to keep it the same slope, but that definitely would change the hydraulic of the system. If you go the smaller slope, obviously you can carry less flow, more resident time. If you go with the higher slope, obviously flow go faster with the same discharge. You're going to deal with the less resident time. That would reduce your efficiency. So a slope was basically as recommended by Caltrans. I guess in our experiment, we ran it for 40 minutes. So obviously, it didn't change with time much. But if you are referring to the clogging issue again, definitely we have to run the experiment for many, many days or so. Again, we ran 30 different experiments, but that 33 was the fruits of the result. We ran probably more than 200 different experiments to get to 30. We didn't see a trend in the clogging in our system, even though we basically injected, let's say, how many pounds of sediment, probably a couple of 100 pounds of sediment we injected to the system. Still, we didn't see a trend in clogging. But in long term, definitely, that's a matter of investigation. So that was a pilot project that was funded by NCTCOG. Plan was to do investigation in the lab, and then the next phase, if you get funded, to install this bisoil outside, one-to-one scale, and then monitor for long term. Yeah, we do have the plan to do it. We are trying to get the things funded. We have some talk with some cities. They have some locations, but definitely any project requires some funding in terms of implementation, and doing it in the lab is much cheaper, as I mentioned, but in the field is more expensive, definitely. But definitely there are some interest from City of Arlington. They have some location, they want to install it. I don't know because they ask us to come up with some recommendations with regard to design of soil, and the recommendation, you can find them if you scan this code. At the end of the report, we talked about recommendations, but if they are going to implement it in the future stormwater design manuals or not, I don't know. Hopefully. But definitely, as I said, this was just a pilot project. It doesn't mean that we can just go directly to the design manual guidelines. It should be tested probably in the one-to-one scale. But definitely that's something is required.